Well, hey everyone. So today we're going to go over solving an exact differential equation. So this particular differential equation is an initial value problem. So in our video today, we're going to go over verifying whether an equation is exact, the problem solving methods for solving an exact differential equation, and then solving the initial value problem. So without further ado, let's jump in. So we have our differential equation here, the quantity 3y squared minus t squared divided by y to the fifth power, multiplied by dy over dt, plus t divided by 2y to the fourth power equal to 0. And we have the initial condition that y of 1 equals 1. I want to point out that this is not quite yet in the format for an exact differential equation because of this dy over dt factor right here. So what we're going to do to get it into our form is multiply through by dt in order to cancel out this dt factor right here. So I'm going to do that first. And what I'm left with is 3y squared minus t squared divided by y to the fifth power. Don't mix up your t's and your y's. So multiplied by dy plus t over 2y to the fourth power times dt equal to 0. Okay. So now this is in the format for an exact differential equation because you have a multivariable function times your dy differential plus another multivariable function times your dt differential. Okay, so the first thing that we're going to verify that this is exact is we want to verify that the partial of m with respect to t equals the partial of n with respect to y. Now, what in the world are m and n? Well, m is going to be the function that lives in front of dy. This is your m of ty. And then this is your n of ty. So m of ty, just to be clear, is 3y squared minus t squared over y to the fifth power. However, for the purposes of taking a partial derivative, I'm going to simplify this by writing it as 3 over y cubed minus t squared over y to the fifth. All I did there is just divide each term by y to the fifth power. Okay, and then our n of ty is going to be t over 2y to the fourth power. So let's go ahead and verify that these two partial derivatives are equal to each other. So partial of m with respect to t is equal to the partial with respect to t of the function 3 over y cubed minus t squared over y to the fifth power. Now, when taking these partial derivatives, it's important to remember that since I'm differentiating with respect to t here, every single y term is viewed as a constant. So 3 over y cubed, that's going to be viewed as a constant. So when I take the partial of that, it will be 0. Now, when I take the partial with respect to t of t squared over y to the fifth, since there's a t here, this is our only varying term. So again, this guy is going to be 0 because there's no t's there. This guy, we're just taking the derivative of the t squared. So this is going to be minus 2t over y to the fifth power. So we get negative 2t over y to the fifth. Okay, so that's your partial of m. Let's check now the partial of n with respect to y. So that's going to be the partial with respect to y of t over 2y to the fourth. When differentiating something in the denominator, I find it easier to consider a negative exponent. So this is t over 2 times y to the negative 4. And just using your power rule, this guy moves downstairs, and we get negative 2 t y to the negative 5, which happens to simplify to negative 2t over y to the fifth power. So these two partial derivatives are the same. So this is an exact equation. And that should make you very happy because you can now solve this differential equation using exact equation techniques. Okay, so what does that mean for us? Well, let's get into the solving. So solving the equation, basically you're going to pick either one of the functions to work with. Pick m or pick n. It's dealer's choice at this point. So I'm going to choose to work with m. And what we're going to do is say that the partial of some function f of x, y, or in this case, partial of a function f of t comma y, the partial of f with respect to y is going to equal m of ty. So I'm starting here. So the partial of f with respect to y is equal to our function. I'm going to use the simplified version, 3 over y cubed minus t squared over y to the fifth. You're going to find that you work with a lot of functions in this section of differential equations, so you might have to refer back to previous work, so just make sure you write out detailed work. Okay, so, and by the way, f is equal to some function f of ty. Okay, so that's what we have in the back of our minds. So what we're going to do first is we're going to integrate with respect to y. So integrate this function with respect to y. So the integral of the partial of f with respect to y is going to come out to be f of ty. And this is equal to the integral of 3 times y to the negative 3 minus t squared y to the negative 5. And again, I just like considering the negative exponents for the purposes of differentiating or integrating. So integrating this term by term, the integral of 3y to the minus 3, we add 1 to the exponent and divide by that same number. So you should get negative 3 halves y to the negative 2. Minus, let's integrate this term right here. Same process. We add 1 to the exponent on y and divide by that same number. So that's going to be t squared times y to the negative 4, adding that 1 to that exponent. And we divide by that same number. And just note, dividing by a negative makes this term positive. So this is what we have. And now don't forget your quote unquote plus c here. And I say quote unquote because we had integrated this function with respect to y. However, it should be known that f is a multivariable function. So rather than giving a general constant in other words, a number here, we're going to consider our constant to be a function of t. So I'm going to call that function h of t. Okay. Now, why did we do that? Well, the next part of solving for this is saying, let's find the partial of f with respect to t. Well, the partial of f with respect to t is equal to the partial with respect to t of the function that you just found. So I'm going to copy that over. And this is what we are differentiating. Well, the derivative of negative 3/2 y squared, this guy would zero out. So the partial with respect to t of negative 3/2 y to the negative 2 will just zero out. The partial with respect to t of t squared times y to the minus 4 over 4. And then the partial with respect to t of h of t. What we're going to do is on our t squared term here, we're going to use power rule and differentiate like that. So what we have is 2t times y to the minus 4 over 4 plus the derivative with respect to t of h of t. We don't know what h is, so we're just going to call this h prime of t. So we cancel out this factor of 2 here, and what we're left with is t times y to the minus 4 divided by 2 plus h prime of t. Or without the negative exponents, we're just going to say that this is t over 2y to the 4th plus h prime of t. So the reason why we did this is our main roadblock in this solving process, because it felt like we solved it here. The roadblock is that we don't know what h of t is. So finding this partial here is our next step in figuring out what h is. And so why did I take the partial with respect to t? Because the partial of f with respect to t, just like I said that the partial of f with respect to y is equal to our m of ty, the partial of f with respect to t is equal to our n of ty, which was the, if I scroll back up to the very beginning, n of ty was t over 2y to the 4th power. So what we're going to do is set these two equal to each other. We're going to set those two equations equal to each other and solve for h. So what I have is t over 2y to the 4th power plus h prime of t equal to t over 2y to the 4th power. And we're going to solve for h of t. Well, I'm going to isolate the h prime term. And I get that h prime of t equals 0. And this is fairly nice because I can integrate both sides of this with respect to t. I'll find what h of t is. And the integral of 0 with respect to t is just a constant. Now I will get just a constant here when I do this because h prime of t equal to 0, I'm equating two one variable functions at this point. So that's why I'm getting a constant here. And by the time you get to here in an exact equation, you should be dealing with a one variable function. So this is great because we have now figured out what h is. It's just a constant. Now, in any event, what you want to do is actually set your f of ty equal to a constant. That's your implicit solution for an exact equation. So what we're going to have is our, let's see, it was -3/2 y to the minus 2 plus t square y to the minus 4 over 4. This is just going to equal the constant h of t. Now, I like my solutions without negative exponents, so I'm going to rewrite as 3 over 2y square, or -3 over 2y square plus t square over 4y to the 4th. But that is our general solution. Now, you're not done with the problem just yet. This was an initial value problem, so we do need to apply our initial condition. And the initial condition was given at the very beginning of this problem. It's y of 1 equal to 1. So I'm going to write that down here. Y of 1 equal to 1. And it's always lovely for teaching purposes when your t and your y are the same. So for the purposes of keeping track of what is what, the green one is t, the blue one is y. So we're going to plug these into our solution to figure out what c is. So we have -3 over 2 times 1 squared plus 1 squared over 4 times 1 to the 4th power equal to c. So -3/2 plus 1/4 is equal to c, and that would end up being -5 over 4. Okay. So with that, that is your constant for your solution. So your final answer to this initial value problem is -3 over 2y squared plus t squared over 4y to the 4th power equal to -5/4. Okay, and that is solving an initial value problem with exact differential equations. So I hope you found this video helpful. If you have any questions, just leave them in the comments below. And that's all for now, folks. Please like and subscribe. Have a good one. We'll see you in the next video.